Welcome back to Professor Explains. Today we're going to discuss one of the most important and often most confusing topics in radiographic physics, kilovoltage peak or kVp. Many students struggle with kVp because changing this one exposure factor affects multiple image quality factors simultaneously. I want you to think of kVp as the beginning of a chain reaction. Every time you increase or decrease kVp, a predictable sequence follows. Starting with kVp. kVp affects beam quality. Beam quality affects penetration, attenuation, subject contrast, and patient dose. kVp stands for kilovoltage peak. kVp is the voltage applied to the cathode and anode, creating an electrical potential difference between the electrodes inside the X-ray tube. Voltage is the electrical pressure applied to the free electrons. The higher the electrical pressure, the harder the electrons are pushed from the cathode and pulled toward the anode. Think of kVp like the gas pedal in a car. The harder you press the gas pedal, the faster the car moves. Similarly, increasing kVp accelerates electrons more forcefully. The electrons accelerate, gain kinetic energy, and strike the tungsten target. Two X-ray production interactions occur at the anode. We'll explore each of these interactions in detail in a separate video. First key relationship. kVp controls the energy of X-ray photons. Higher energy photons have higher frequencies and shorter wavelengths. Frequency is the number of wave cycles that pass a point each second, while wavelength is the distance between two successive wave crests. Because frequency and wavelength are inversely related, as frequency increases, wavelength decreases. As photon energy increases, the X-ray beam becomes more penetrating. Now let's talk about beam quality. Beam quality refers to the penetrating ability of the X-ray beam. A beam made of higher energy photons has better beam quality. Think about trying to throw a tennis ball through a stack of cardboard boxes. Now imagine throwing a baseball. The baseball has more energy, so it travels farther. X-ray photons behave similarly. A 60 kilovolt beam contains lower energy photons. Many are absorbed before they reach the receptor. A 100 kilovolt beam penetrates successfully. This is called greater penetration. There is a direct relationship between beam quality and penetration. When beam quality increases, penetration also increases, and vice versa. This relationship is tested frequently on examinations. As X-rays pass through the patient, they don't all make it to the image receptor. The loss of beam intensity is called attenuation. Attenuation happens in two ways. Some photons are absorbed by tissues, others are scattered, changing direction instead of continuing straight. At lower kVp, photon energy is lower. Many are absorbed within the patient's tissues, producing greater attenuation. When kVp increases, photons have more energy and pass through. So increasing kVp leads to less attenuation because more photons penetrate through the body to reach the image receptor. Let's see how this changes image contrast. Subject contrast is created because different tissues absorb X-rays differently. On the left, the image was produced using a high kVp technique. Notice that there are many shades of gray between the bone and surrounding soft tissue. This is called long-scale contrast or low radiographic contrast. Because the X-ray beam has higher energy, more photons penetrate the patient, reducing the differences in attenuation between tissues. Now look at the image on the right. This radiograph was produced using a low kVp technique. Here the bone appears much brighter, the soft tissues appear darker, and there are fewer shades of gray. This is known as short-scale contrast or high radiographic contrast. Lower energy X-rays are absorbed more readily, which increases the difference between structures. At low kVp, these differences are very noticeable. Bone absorbs more photons while soft tissue allows them to pass. Now increase the kVp. Higher energy photons penetrate both bone and soft tissue more easily. The difference in absorption becomes smaller, and the image has many shades of gray. This is why kVp is considered the primary exposure factor that controls subject contrast. The 15% kVp rule is a fundamental exposure principle in radiography that describes the relationship between kVp and receptor exposure. Increasing kVp by 15% causes receptor exposure to double. Conversely, decreasing kVp by 15% results in 1/2 the receptor exposure. Let's look at a practical example of the 15% rule. Suppose your original technique is 70 kVp and 20 mass. If you increase the kVp by approximately 15%, the new setting is 81 kVp. This increase by 15% doubles receptor exposure. To maintain the same receptor exposure, the mass must be reduced by half from 20 mass to 10 mass. The result is 80 kVp and 10 mass. This change to each factor is inverse and not directly proportional, yet will maintain similar receptor exposure. The 15% rule is one of the most frequently tested concepts in radiographic physics. In many exams, using high kVp and low mass results in less radiation dose to the patient. This is a key exposure optimization strategy and an important concept that applies to the ARRT principle, keeping radiation exposure as low as reasonably achievable. Let's review the sequence one final time. When kVp increases, photon energy increases. Higher energy photons create a beam with greater quality. A higher quality beam penetrates the patient more effectively. Because more photons pass through, attenuation decreases. This produces lower subject contrast and more shades of gray. Finally, when we reduce mass and increase kVp using the 15% rule, patient dose may also decrease. Study these relationships, not just the definitions. Once you understand how one change leads to the next, you'll be able to reason through many exam questions. If you found this helpful, please like this video, share it with your classmates, and subscribe to Radiography Professor Explains. Have a question or a topic you'd like me to cover next? Leave a comment below. I'd love to hear from you.